Oh, before I give over to Wang, I'll give him a brief introduction. So this is Wang Ling. He works with our language processing group at DeepMind. Wang's originally from Portugal. He actually did his PhD in there's this nice joint Carnegie Mellon University in the US and Lisbon PhD program that Wang came through a few years ago. And recently he's been working with us at DeepMind on lots of interesting deep learning and language problems. But he does have a particularly nice introduction to neural networks for you, so I thought I'd get him to give that lecture for the first lecture today. So, thank you, Wang.
Okay, hello. So my name is Wang Ling, and this will be an introduction for deep neural networks. And this is the outline of the first part of the talk. So you can see that we'll pretty much cover everything that you need to learn about math. So if you don't understand this, I would be worried. And then once we cover everything, we'll go into deep learning and talk about some of the models, at least the simplest ones that you should know if you want to work on deep learning. So the first thing that we learned in elementary school was numbers, and once we learned about them, everyone became happier, because if you want to answer that question, you can say 4 instead of just showing, okay, this many apples. Sorry. And then we learned about variables. So, well, we did not learn about variables directly, but we learned that 4 apples are different than 4 bananas or 5 bananas. So we can associate numbers, quantities to different concepts and give them labels. And then we learned how to operate on these numbers. So basically, if we say that if Abby has 4 apples and gives 1 to Bert, then we can just do a simple subtraction and say that, okay, after she gives 1 apple, she will only end up with 3 apples. And then we finally learned about functions. So let's say that that Bert says that for each apple that that Abby gives to him, he will give her 3 bananas. So what's the function here? And basically, a function is a process where you have the x, which is the input of the function, and then you are given, and that yields an output, which is y. So basically here, x is the number of apples that Abby will give Bert, and y is the number of bananas that she will get in back. And this is where it gets interesting. So now that we have the function, pretty much we know exactly, given any x, what's the y that you obtain. So in this case, if x is equals to 1, she will get 3 apples. So we can say that that function perfectly models what Bert is going to do given the number of apples that Abby gives her. And if you think about it, pretty much everything that we do is more or less what a function. So like translation basically is a process where you take an x, which is the input. So you feed the input sentence in English. And for instance, if you want to translate into Spanish, you are expecting to receive a Spanish sentence, which is the translation of x. Like if you want to, does anyone know about this? So basically DeepMind was working on a Go system that basically beats one of the top Go players in the world. And basically the system that you want to build is a function where x is a board state, so the current state of the board, and you want the system to give you the next move. Finally, like in image classification, x is going to be an image, like this cat here, and basically you want to classify it as either cat or anything. So basically, if you have a function, pretty much you have solved it. If you have the correct function, you have solved the problem. But the problem here is that this is really hard in most of the cases. So, for instance, in translation, the first translation systems, people don't use machine learning. They actually write rules to actually say, okay, this is a sentence, let's do this, and then that gives the translation of the sentence. And this system actually works. But just that later on, people found out that if you use machine learning, you can do much better. Let's talk. So let's talk about a different kind of function. So let's say that now Bert is gone and we have the Cookie Monster. And instead of telling us what the Cookie Monster is going to do, he's going to make us try to find out how many bananas he will give Abby after she gives him apples. So what she's going to do is that she's going to give him 1 apple and then she gets nothing back. Then later she gives him 5 apples and the Cookie Monster gives her 16 bananas, and then she gives 6 apples and receives 20 bananas. So Now she ran out of apples and wants to find out if she gives the Cookie Monster 3 apples, how many bananas will she get back? So to do this, before we had the function like that, we need to add a new type of variable which we call parameters, and that is what makes the model. So our model will need to have parameters. And the difference between the input and output is that the input and the output is what we observe in the world. So these are things that happen that correspond to reality, while parameters are something that need to be estimated. So based on what we see, we need to find the parameters that will give us the correct results. So let's say that right now we will model the Cookie Monster using that model there, which is y equals wx plus b. And what we are going to say that the data is what we have observed, and we want to train a model using this data. So basically, you can represent the data in this table, which is, well, the values of x and the values of y. So now we have the data and the model. So what else do we need? So how can we actually, so now we need to find the parameters w and b. So how can we do this? So the first thing we need to do is that, given that I will give you some random number for w and b, and these are the y's that it would get. So basically, this, if you plug in the input data into the current model, these are the values that you would get. And now I will do this again with a different parameterization, so different values for w and b, and that is the value that you would get. And the question that we want to ask is, which one is better? And until we can actually answer this question, there's nothing we can do, because we cannot evaluate which model is better. So we don't even know what's the meaning of the model being better at this task than another model. So what can we do? Oops. Okay, so we need to define a cost, and the cost is basically what's going to tell us, given the parameterization w and b, how good or how bad is the model. And one possible cost function is what we call squared loss, and basically we are going to take the actual answer and subtract the answer that the model got, and we are going to square it so that it's always higher. So in this case, the higher you get, the more different the answer of your model and the actual answer is. And now we are going to compute this. So we'll take the first two values and compute the difference. We take the second row, do the same, and take the third row, and add them together. And that will be the cost of the first candidate model. So, and that's like 318. We do the same for the second model. And basically, the one that gets the lowest score is the better model, because the lower the cost, the closer you are to the actual solution, given this cost function. So basically, this is the model we want. But now we ask the question again, how to answer the parameters, how to actually find the best parameters, w and b. And for this, we need the optimizer, because whereas you can keep trying different values of b and w, finding the best values that will give you the optimal cost, which ideally is 0, is not a simple problem. So basically, the formal way to say this is that we want to find the minimal value of the cost for all possible values of b of our parameters, which is w and b. So because we only have two parameters, we can draw this in a plot. So w is the y-axis and b is the x-axis. And let's take the first point that we already got and start from here. So we draw that point in the graph, and so that's where it is. So it's like 2, 2. And how can we actually look for a better value? So we can just simply start trying different values. So let's say that we add 1 to w and compute the cost function for this. So we draw the table again, and now we have 26. So 26 is better, so let's just keep this one. And now we start from the new point and try to find another point. So let's try adding another 1 to w and compute the cost function again. So now the cost is like 136, so it's not good. Then we don't go there. So we try to increase b and compute the cost function again. And once again, it's not as good as the one we have right now, so we don't do it. And then we try to subtract b, and now it's a little better. So now we advance once more to the new point, and we keep doing this. So if we subtract more, it will get better again. Okay, so and we keep doing this. So at this point, you can see that if we go left, the cost will be worse. If you go down, the cost will be worse again. And if you go up, the cost is worse. So technically, the algorithm would have to stop here because there's no way to find a better point at this point. So is this really the end? And the answer is no. So if you take that point over there, the actual cost of that function is actually 12. So it's lower than the cost that we have right now. So why can we not find this point? So basically, it's if you look at this as a search space, you can see that the points that we sampled to test if the model was better are actually worse. But there's a narrow path in the middle that actually leads you to that point. But so basically, it's not like the model cannot do better. It's just that our optimizer is not good enough. So this is what we call a search problem in machine learning. So even though the model can do better, we cannot find the parameters that will make the model do better. So what are the solutions? So one thing we can do is to actually make the step size smaller. So instead of adding 1 to one of the parameters, we add something very, very small. And basically, if we do this, you can see that the model will slowly reach that point. So one thing that you generally have to decide when you train models is that you can either take a very large step size, like we did in the beginning. And the good thing about this is that you will get to the point much faster. So if you take a very small size, your model will take much longer to train. But the problem is that it might not yield optimum that's as good. While if you take a very small step size, you generally get a better optimal, but it will take you very, very long to do this. And what people generally do is to actually start with a very big step size. And once your model stops improving, you just reduce your step size to half and keep going. So you already got to a very good point, but you cannot do better. Now let's go slower. OK, so now if we do this, eventually we'll get to that point over there. So if you keep applying this model again, at some point you'll find the point 0. And because this is a linear function, you always get there if your step size is small enough. So if we say that W is 4 and B is minus 4, you will get every sample correctly. So with this, we can actually have our model, which is 4 and minus 4. And you can predict that if Abby gives the Cookie Monster 3 apples, she will get 8 bananas back. So basically, how different is the current model compared to things like image classification? So basically, the only thing that's different, and actually there are two things, but the thing that we are worried about now is that you don't really only have W and B. For image classification, for instance, your input is the whole image. And each pixel is one feature. So each pixel has a W associated to it. So if you want to classify 40 times 40 pixel picture, you'll have 1,600 different inputs. And each input can have a value between 0 and 256 if it's black and white, or 3 values if it's RGB. So basically, this means that we actually have a lot of parameters. So it's not like we can just optimize the parameters one by one, like we did. But I mean, this works if you have 2 parameters. If you have multiple parameters, it doesn't work. And in general, image classification data sets are trained on over millions of samples, not only 3. So this basically means that if you want to compute that cost function there, so for instance, when you are trying different values, computing that will take you a lot of time. It's generally a few hours or a few days, depending on how big the data set and how big your model is. So we cannot just afford to test each different parameterization by computing that function. So how can we do this by using as minimal computation as possible? So let's start from that point again. But instead of just trying different values, let's define a vector, which we will call h of w, and say that that's the direction of the step size. And let's say that for now, h of w is 1. And what we want to do is to say, OK, so if the cost of hw of the current values plus that vector is 26 now, so once we take that step, we'll get to 26, we can compute how much based on the distance that we travel, how much each unit towards that direction will reduce the cost function. So basically, I call this reward, basically. So it's how much you walk divided by the length of what you walked. And so if you keep reducing this, you can see that the values, so if you keep reducing this, the amount of reward that you get, you can see that it converges to a value. And this is because this is basically the definition of the derivative of the cost function with regard to w. So basically, a derivative of a function with regard to that variable is basically what will happen if you take an infinitely small step towards that direction. So basically, what this means is that we only have to compute the derivative of the cost to know which direction we actually need to go to make the cost become smaller. So if we derive that function according to w, we'll get this value here. So basically, it's just like taking that, plugging that equation there and deriving it. And then we can see that if we actually derive and compute the value of the derivative, it actually gets to minus 104. The calculations are there, just in case. So now, if I want to know which way to go, I don't really have to compute the cost function and try for each direction. I just compute the derivative and plug in the current points, the current parameters there, and I know exactly which way I need to go. So, for instance, in this case, for these two, for this position here, I know that if I take an infinitely small step towards h of w, I will reduce the cost by minus 104 for each step, and if I increase b, I will reduce it by minus 12. And suppose that these numbers are actually positive. That means just that instead of increasing it, I just need to reduce it. So once again, basically, this is what we call the gradient descent algorithm. So we take at each iteration, we take the current values of our parameters and subtract the reward function for that parameter plus the alpha. And alpha is once again a step size. So once again, if you take big alphas, then you'll get to the minimum faster, but it will not be as good. And if you take small steps, it will take longer. But basically, this is, so you don't have to try every parameter. You just have to compute it once for each iteration now. And that's pretty much it. So this is basically the summary for what you need to know about basic machine learning to understand deep learning. So basically, you have the data, which is what you have seen in the world. So this represents what the real evidence of how to solve your problem. Then you have to define a model. In our case, we define a linear model, but you can decide what kind of models you have. And as you learn more about deep learning, you understand that there are many, many different models that you can apply. Finally, once you have the model, you need the cost function to know how good a model is. And then you have to have an optimizer. And all of these, except the data part, people work a lot on how to define better models, how to define better cost functions, and how to define better optimizers. So there's a lot of research happening in each of these fields. And once you have all of this, then you can build your own system. So you train this, and you build your system, and that will give you the whatever function that you want. So now we go towards deep learning. So we are first going to start talking about nonlinear models. And so basically, the function y equals 4x is minus 4 is linear. So the more apples you give, the more you will receive. And if it's inversely proportional, the more apples you give, the less you will receive. But it's going to be proportional in some way to your input. But the problem is that most of the phenomena that happen in real life, they don't tend to be linear. So it's not like if I just keep giving if I give him like 200 apples, he will run out of bananas to give me, for instance. So he might not just give me that many bananas. So let's try to model this. So what the Cookie Monster will say is that if you give me too many apples, I cannot give you the equivalent of bananas. So there will be a point where I'll stop giving you bananas back. So before, our function is like this. So this is the y, this is the x, and those are the points that we have already drawn. And we are going to add 2 more points. And so Abby is going to give the Cookie Monster 9 apples and still get 20 bananas left, and 11 apples and still get 20 back. So now the problem is that you can see that a linear function can never actually model these data, because there's no way you can draw a line that passes through all these points without missing one of them. So the best thing you can do is this. So if you define that function, and that's the optimal for this data set, so you can only make sure that the line goes as close as possible to each of those points. And this is a phenomenon that in machine learning that we call underfitting. So it's not like you don't have enough data. It's just that no matter how much you train your model and how much data you have, you just cannot model the problem. So the model is missing the expressiveness that you need to actually learn this problem. And this is why you need to learn about nonlinearities. So what we want to do is to learn a function like that. So it goes like straight up until that point, and suddenly it turns right. So is there any way we can actually learn that function? So let's do something like this. So let's use different functions. So let's say that we have two functions that we are going to model. One that uses parameter w1 and one uses parameter w2. And there are like some binary vectors like s1 and s2. And we want s1 to become 1 if x is inferior to 6. So it will activate the function that grows up. And we want S2 to be 1 if x is superior to 6, so that it stays constant. And if we could do this, we only have to define this function here. So it's like 4x minus 4, which is what I had before, until it goes to 6. And after it goes to 6, it just stays constant. So is there any way we can actually learn S1 and S2? So let's see how we can actually do this. So I guess the most obvious nonlinearity that you can have is what we call the logistic sigmoid function, and that's basically that function there. So basically, you take 1 divided by 1 plus the exponential of minus t, which is your input. And the important part is not to understand the function, but see how it looks like. So it's basically ranges between 0 and 1 in the y-axis. So it can take any value between 0 and 1, and has your input x goes towards minus infinity, it goes it converges to 0, while when it goes to plus infinity, it converges to 1. And this lets us do a lot of things, like how to define these Boolean operators. So one thing you might want to do is what we want to do here is a flat function. So for instance, we want something that as soon as goes to left of 6, it goes straight to 0, and as soon as it goes to the right of 6, it goes to 1. And basically, you probably learned in high school that if you take a function and multiply the input by a very large value, you basically squeeze the function. So what the function will look like is like this. So as you squeeze that sigmoid function more and more, you get closer and closer to the flat function, which basically is like 0 and 1, depending on one value, on one interval. So here, if you do this, if you compute the sigmoid function with x equals to 0.1, it will basically be very close to 1. And if you compute the sigmoid function towards minus 0.1, it will be very close to 0. And if you want to shift the function towards 6, you basically have to subtract whatever value you want to shift. So here, you want to shift by 6, so you subtract x times, you subtract 6 to x, and that becomes 6,000 because of the multiplier. So now we have a function that basically, if it goes to the left of x, it will be 0, and if it goes to the right of x, it goes to 1. And I'm just trying to show you how you can actually use nonlinear models to learn this. I mean, your model eventually will have to learn something like that, but it depends a lot on the optimizer if you can get there. But you can see that this is possible using this model. So now what we have is a model that looks like that. So you have two linear functions, and they are like multiplied by two nonlinear functions, which can go from 0 to 1. So basically, and the trigger is basically whether x is to the left of 6 or to the right of 6. So just to show you how it would work, if you take this value here, then x is equals to 5, so that will be 16, that will be 20. And the first sigmoid function will be 1,000. The second sigmoid function will be minus 1,000. And basically, this means that we will activate the first function and not the second one. So the second one will be nullified, basically. So we still get the value 16. But if we go to the values above 6, you can see basically that it's 32 there and 20 there. But now the activation functions will be the other way around. So now the second a linear function activates, and that gives us the value that we want. So you can see that we can define this function this way. Let's try to make it a little harder to see how far we can go with this model. So now we will say that if Abby gives him even more apples, he will get upset and just give you one banana back. So it will look more or less like this. So if you go to 15 and 19, he will just give you one apple back. So how do we learn this? So basically, the function is still more or less the same that we want. So the function that we want to achieve is still more or less the same, except that we have like the two sigmoid functions. We check if it's below 6 or if it's above 15. But there will be another sigmoid function that needs to check for whether it's in the interval between 6 and 15. So how can we actually do this? And basically, what we need to do is to say that we want S2 to activate when S1 and S3 are not activated. So basically, the way we can do this is to actually plug in S1 and S3 into S2. So basically, S2 is dependent on S1 and on the values of S1 and S3. And for instance, if we do, and basically, if you are in the language of multi-layer perceptrons, where like S1 and S3 would be layer 1 perceptrons, S2 would be a second layer perceptron because it depends on the values of the first layer perceptrons. So the way we can do this and make this work is to say, for instance, that you say that it's minus 1000 S1 minus 1000 S2, so that the only way that S2 will be positive or have a big value is if both S1 and S2 are 0. If either one of them are actually not 0, then the value will be negative because the bias is on 500. So let's say that we take this example and see what the value is. We will get like 40, 20, and 1 on the first line. And here we see that both are not activated. So they are 0. And if we add 500, we will just get something that's very high. And that will lead us to 1. So the middle function will actually activate. So basically, this gives us the correct value in that interval. And if we take the number 19, you'll basically get the results that we want. So we want the third function to activate. So the first and third sigmoid functions will give you 0 and 1. And because the second is 1, this value here will be minus 500, which will be 0. So the third function will activate. So yeah, so you can see that by doing this, you can actually get the correct function. So you can see that pretty much every function that you can define, you can just use these intervals to actually define. You can actually memorize each of the x's. And in terms, and just a notation, something about notation. So basically, it's very confusing once you have very big networks to actually define everything in terms of equations. So what people do is to say that you have the input, you draw a graph where each node is like one variable, and wherever there's a dependency edge from one variable to the other. So for instance, in x to S1, that means that S1 is like a linear combination of the value of x times a parameter plus a bias. So you can do the same for S2, and so because S3, because S2 depends on S1 and S3, you say that you draw an edge between both of S1 and S3 to S2. And if you look at what's happening on each of the perceptrons, you can see that the first layer perceptrons can only learn things like boundary conditions, like is x inferior to this number, is x inferior to this number, while the layer afterwards can learn intervals, basically. So can you actually learn something, because by combining the first layer perceptrons. So basically, you can do something like this, and you can just learn more. So multi-layer perceptron generally has multiple layers, and each layer learns like more and more complex conditions. And basically, when you define a real multi-layer perceptron, it looks more or less like this. So you define the number of units you want in each layer. So here we will say that there's the input, and the first layer will learn something about the input features, and the second layer can learn combinations of the input features. So you can basically combine input features like is is feature 3 activated or feature 2 activated at the same time, or is one of them activated. And by doing this, you can basically learn these functions. So it would look something like that. Of course, you will not see these high numbers in a neural network, but but this is like a rough example of how would you accomplish an OR and an AND condition. And the only thing you cannot do with two-layer multi-layer perceptron is XOR conditions. And for that, so basically XOR is like if one is activated or the other one is activated. And for that, you can just use the definition of an XOR and basically use combinations of ANDs and ORs to actually accomplish the third layer. And once you have this, pretty much you can learn any kind of conditions that you want. And we call a multi-layer perceptron a universal approximator because if it has enough units and it has more than 3 layers, pretty much every function that you can learn, it is learnable by multi-layer perceptron. But the problem is that it doesn't mean that it will learn the correct function. So even though you can learn any function, because you can have so many conditions, you can just learn a function that looks like that. So it basically does not have to, it does not have to generate the behavior that you expect. So for instance, how could it do that? So for instance, let's say that we want just to memorize pretty much every answer. So we can have a network to say that if x is higher than 1, and basically produce the first output. If x is like between 5 and 6, produce that, activate that unit. And if x is superior to 6, just produce 20. And basically what the network is learning is like memorize for each input what is the output. So basically it's not learning anything, it's just like memorizing your data. So this is not very useful. But if you give your network enough layers, it will be able to just do this. So this is what we call the problem of overfitting in machine learning. And this is a model problem. So basically, whereas underfitting is when your model is not expressive enough to learn your data, overfitting is when your model is expressive enough but learns a wrong function, because the more expressive the model is, the more wrong functions it can learn. So a way to illustrate the problem is that underfitting is when your task is too complex for your model. So if your task is too complex for your model, you will not be able to, the model will not be able to learn it. So you don't want to be there, but you don't want to be here either. If your model is very complex, but your task is not very, very hard, then the model will be able to actually just learn some function that's ridiculous. So you want to be like somewhere in the middle. So depending on the task complexity, you want to have a model that's just good enough to actually produce that task. So you want the correct functions to be within your model's ability to generate, but not have too many other ways to generate a model that can fit the training data. So for instance, if you are talking about model complexity, examples would be like linear regression would be something that's very, very similar. It's that y equals x for x minus 4. So it's not very, very good at modeling. So it's very prone to overfitting. But for instance, if you add more features, if you add other values, it will become more complex. Another way, but things like multi-layer perceptrons can get much more expressiveness as you add more layers. So then you will get the danger of overfitting. So in terms of task complexity, things like sentiment analysis tend to be a simpler task, while things as machine translation tend to be much more complex. So you need much more parameters and hidden layers to learn machine translation, whereas in sentiment analysis, the task is simpler, so you generally don't need as many parameters. The other thing that it's important to take into account is the amount of data you have. So if you have very little data, then you will be under a lot of like stress of overfitting. But once you get a lot of data, then overfitting does not become a problem at all. And the reason, and one way to think about this is that the more data you have, the less ways your model can overfit, because there are less wrong functions. So for instance, if you have those points there, and let's say that only the right one is the correct function and the first two are wrong, if you add one more point, you can see that the first function cannot actually fit all the points anymore. So because the points actually represent the real ones, incorrect versions of the model will not be able to fit more points. So as you have more points, the less capacity will the model have to actually choose a wrong way to fit your data. And the other thing that you can work on to actually solve the overfitting problem is to add bias to your model. And things like L1 and L2 regularization would help you to do this. For instance, what regularization tells you is that your model does not have to work very hard to get the answers correct. And so more formally, you have your loss function, you have your cost function, but you can add something that basically says that if the sum of your W and B gets higher, then you get penalized. So the more weight you put on your parameters of your model, the worse the model will be. And what will happen is that it will encourage the model to actually not use as many units as before, because using a unit will require a model to raise its cost. So if you can learn the problem without using as many units, you get a benefit in terms of the cost of the function. Okay, so now I'm going to talk a little about how to use discrete variables. So when you are working on things like bananas and how many bananas you get from apples, your values are continuous. So your input is a number and your output is another number. But when you're working with language, for instance, your input is a word, and we need to find a way to quantify the word in terms of numbers. So one way to do this, so what we are going to do here is that now we are going to say that Abby can give the Cookie Monster a fruit, but it also has to choose what type of fruit it can actually give. So you have a discrete variable here, which is the type of fruit, so which you cannot quantify in numbers. And in the same time, the Cookie Monster will have to return a fruit and a number of instances as well. So on both sides, you have discrete variables. So how would we do this? So right now, our model looks like this. So it has the number of fruits that Abby will give, and it returns a number of fruits that and the Cookie Monster will give back. But now we are going to, we are going to just draw them all like this. So basically, these are the layers of a multi-layer perceptron, just because it's not really needed to show this. And now we are going to add another variable, which is the type of fruit to offer. So basically, U here will define the type of fruit that will be offered by Abby, and V will define the type of fruit that will be given back. And let's say that U can be one of the fruits in that set. So it's either an apple, a banana, or a coconut, and V is also in the same set. So what people do in generally neural networks is to say that we need to have values. We'll have parameters for each of the types of fruits. So basically, like apple, we'll set that it's parameterized by 4 parameters. So it's E1, E2, E3, and E4, and each different type of fruit will have a different we'll have a different set of parameters, and these has other parameters will be trained when you are training your model. And once we know because we know what fruit is in the input, we just take the correct row. So if we want to give apples, for instance, we will just take the first row and put it in the embedding U. And if you want to take something else, if you want to take bananas, we'll just put that in the embedding U. So embedding U will be that vector. And that will be a vector of numbers. And this will be fed into the input there. So basically, now the sigmoid functions will have 2 inputs to work with: the embeddings of the banana and the number of the embeddings of the banana and the number of bananas that will be given. And these are combined the same way as you would do with just one parameter. But so you will be able to learn you'll be able to learn the interactions between each type of object, each type of fruit, and the number of fruit of that fruit that will be given. So on the output, so it's a little different because we don't know which is a fruit that will be given, but we want to maximize the probability of that fruit. So what will happen again is that we have the input vector, which is also size 4. We will have to produce one value for each of the types of fruit that will be given. And this is what we generally call logit. So because we have like 3 different fruit, we'll have like 3 different values in that vector there. And so it looks more or less like this. So in the input, it's like the size of the sigmoids, and on the output you have 1 value for each type of fruit. So D1 could be apple, D2 could be banana, and D3 could be coconut. And then you want to convert this into a probability. And the way you do this is to apply the softmax function, which is basically you take each D and the exponential of each D and divide by the sum of each possible logit. So basically there you take the exponential of 1 and divide by the exponential of all of the logits, and you compute this for each of those numbers. And this will give you a nice property, which is like the value will always be between 0 and 1, and the sum of all of them will be 1. So it's something that emulates a probability. And suppose that we actually observed that and the Cookie Monster gave an apple back in that case. What will happen is that because of that division, not only the model will update itself so that the probability of the apples will get higher, but it will also update the other ones to be lower. And basically, so now we can actually build a model that will have the number of fruit and the type of fruit, and we'll also return the number of fruit and the type of fruit that the Cookie Monster will give back. So to summarize, so basically, we explained one of the models that's not used right now, but before it was frequently used, called multi-layer perceptrons. And basically, we talked about how to work with continuous input variables and how to use sparse variables, which are like embeddings, and how to actually yield continuous variables using linear combinations, and how to generate sparse variables using the softmax. So, thank you.